So welcome to breakout session this morning. We will start with the topic analyzing network reliability up to 800G by Thomas Weibler and Dr. Gerhard Stein from FLEXOPTIX. Dr. Thomas Weibler is the CTO of FLEXOPTIX, and Dr. Gerhard Stein is the lead research engineer in charge of ensuring that innovative and amazing prototypes can make it into the market. It is our pleasure to welcome them to NANOG stage today. Thank you.
Thank you very much, Jeffrey. I think I'm on. Perfect. Can you hear me? Good. Yeah, as Jeffrey already mentioned, I'm Thomas Weibler, a CTO and co-founder at FLEXOPTIX. Briefly, the company is really specialized in optical transceivers and transceivers. We only do transceivers, that's our main topic. And we do this since quite a long period of time, roughly 17 years. And yeah, we always try to look up what is possible and doable with transceivers, and also especially when it comes now, the topic we brought today, if you want to do some testing and analysis in your network, actually with the transceiver itself and not with a dedicated testing gear. And we want to demo it later on. Gerhard will show it how it works. So yeah, let's start. So that's a little bit the agenda for the talk now for the next 30 minutes. I do a little bit an intro and a recap. I did a talk last year at NANOG in Charlotte about 400 gig coherent modules. There's a little bit a recap there. And then we go over to the bit error rate dependency. So what is the bit error rate and where are the dependencies? And then we show you results, what we did on either distance or the temperature influences the bit error rate. And then Gerhard will do some live demo, and then we have some takeaways at the end. So let's start first of all with a little bit of the recap. What I presented last year. How do you want to measure link quality, and why is this so important? So as a network engineer, you typically look at a bit error rate of a link. So your goal is to have a low bit error rate because then your link is working properly. And the upper layers, so bit error rate is mainly, we're talking about a physical layer on layer 1. And the upper layers like layer 2 and layer 3, they don't have big issues to handle those errors because they also have some error correction or error handling mechanisms. But we want to avoid bringing errors from layer 1 up to layer 2 and above. The folks who are doing mainly data transmission, like the DWDM, metro or long haul, they do not care that much about bit error rate. They more focus on the signal to noise ratio. So what is the signal to noise ratio? You see this on the lower graph there. On the bottom, there is the noise level. Like in this audience now, it's very quiet, so no noise at all. And then there is the desired signal, which we see with our margin of 25 dB. That's the desired signal. And the goal is to have a big margin between the desired signal and the noise level, because otherwise, if this margin is eaten up, and we are basically talking about 20 up to 30 dB, 30 dB is the maximum we can get, then if it's below 20 dB of margin, then it's very hard for the receiver to distinguish between the desired signal, actually, our zeros and ones, or is it noise? So keep that in mind. But both of them, so the bit error rate and the signal to noise ratio, they do have a close relationship. You will see that later on. A second thing I talked 5 years ago, actually, when the first 400 gig pluggables, so 400 gig was there already 5 years ago or 6 years ago. But as a pluggable module, a new device or a new chip was introduced. It's the digital signal processor inside of a transceiver itself. So the DSP has a couple of functionalities, and the one we are focusing in this talk now is mainly on the SNR, or the measuring of the SNR, either on the electrical or optical side, and the bit error rate testing capabilities. And for sure the DSP does a forward error correction, but it's partially covered today. Okay. So how did our lab setup look like? As I mentioned at the beginning, we didn't use any external tester to generate patterns. So basically, we use the Flexbox we developed. Actually, it's a programming device to program transceivers, but as those transceivers do have the management interface, accessible via the I2C on the back side, on the golden finger side of the transceivers, and we do have the DSP, and we can access this DSP via the I2C. We run some functions on the DSP to generate a bit pattern, for example. Yeah, we needed a little bit external cooling because everything gets a little bit hot because those modules take up to 23 watts and we have to get rid of that heat. So what did we test? We took a whole bunch of transceivers, mainly the latest ones. Let's start from the bottom, like the 800 gig DR8 solution for up to 500 meters. But also we were looking at QSP 112, a 400 gig solution running 4 times 100 gigabit. Then we moved on, looking at regular QSFP-DDs and LR4, for example, or the coherent module. And then you might wonder why there is a 100 gig showing up. Well, as a side product out of 400 gig development, the 100 gig single lambda was kind of a side product developed for 100 gigabit. So it's not 4 wavelengths on that 100 gigabit module any longer. It's just 1 wavelength. But those 100 gigabit modules do have a DSP as well inside, just mainly of the purpose for the modulation scheme which we need there for the single lambda. But we also get the nice benefit that they have analysis functions inside of the DSP to run a bit error rate test, for example. And 2 words about a bit error rate test in general. You might wonder, why is this important? Well, when you think you bring a link online between your gear, typically people look at the TX and RX levels if they are properly, and then they start looking at layer 2 or layer 3 if everything is set up properly. Is the Ethernet framing fine, and also is my IP setup fine? Now, when you can do a bit error rate test in advance, you actually can look, is the link error free? And that's the great advantage, because some errors you might not see without a bit error rate test. And then they will show up later on the Ethernet framing, and then actually it's too late because your link is in service already. And to troubleshoot a link in service is frankly speaking, sometimes a nightmare because there are customers pushing that it's gonna be done soon. Okay, so the first analysis we did on the distance, and the setup looked straightforward. One note here, we do not show all the results because this would last for 2 hours. We just picked out some results of our tests. So the result we show now here is with a 40 kilometer solution doing 100 gigabit on a single lambda way. We used a couple of fiber drums, cascaded them in 10 kilometers and 20 kilometers cascades. And we also wanted to add some attenuation there because we wanted to go to the edge case of the receiver actually. How do those edge cases look like? You see this on the right side. So these are the specifications for the 40 kilometer 100 gig transceiver, and the receiver is typically in the minimum range at minus 14 dBm, and that's actually what we want to achieve. We want to go as low as possible, and so then on the left side you see the table where we did our math and said, okay, in theory we need this type of attenuation to reach the receiver's minimum. And for sure, we also wanted to cover the receiver's max, because on minus 3 dBm, the receiver is in overload, and that's also something you want to avoid. You don't want to get into overload, and in some circumstances, depending on the type of receiver, you will break it anyway. Okay, so the results look like this basically. We were running the bit error rate test out of the DSP permanently on the transceiver, and then we measured on a frequently basis also the temperature where the transceiver is currently, and what bit error rate do we have. And 2 meters, 10 kilometers, and 30 kilometers, and even 40 kilometers, they look pretty nice. So we were at a bit error rate of we didn't hit the maximum of 2.4 multiplied by the 10 by the power of minus 4. And for simplification, I just use now minus 4, minus 3, and so on. So that's actually the edge which is defined by IEEE. So we don't want to go below minus 4 because then this is a bad link. And the interesting part is the green one, the 20 kilometers. We were actually close at the edge of the bit error rate of -4. And when we look at the Rx power, this is something which we actually expected somehow, because the Rx power is at -13.4 dBm. So we are close at the edge of the receiver's minimum. And looking at 30 kilometers or 10 kilometers, we were a little bit above. So you can really see the receiver's power level has a direct influence on your bit error rate where you are. The best one was the back-to-back link with 2 meters and some attenuation at -7 dBm, 7.1 dBm, which was pretty nice. Now you might wonder, what are those weird jumps there with the question marks? Actually, this is a type of the implementation in the firmware made of the transceivers DSP. So depending on the temperature where we are, the DSP does a correction of TX bias because we are looped. So the TX has a direct influence on the Rx. The TX bias is then corrected depending on the temperature where we are running. In software terminology, it's mainly done in a lookup table. So when we reach a certain temperature, we do some correction on the TX bias current, and then the bit error rate improves, basically. And yeah, to sum it up, 50 kilometers was way out of reach because we were also beyond the Rx power minimum. Now, a little bit back to the theory. As I said at the beginning, the 2.4 multiplied by 10 to the power of -4 is the maximum bit error rate which IEEE allows for a proper link. So how is the bit error rate calculated? It's a pretty simple formula. You have the number or the amount of errors you encounter in a certain time, our gating time, and you divide it by the bits, the overall bits you transferred in the same period of time. And now, when we look a little bit in the figures, so we assume 100 errors on a 100 gigabit link, and we have a really great bit error rate of -12, which is perfect. We would call that error-free. Then the gating time of roughly 16 minutes. So every 16 minutes, an error will show up, which is great. Now, when you look at -4, the gating time is going down to 4 microseconds. So every 4 microseconds, an error will show up. You won't see that error later on because the forward error correction will take care about it and correct this and then hands it over to layer 2. Otherwise, yeah, your error count on the layer 2 would got crazy actually. So that's important to know. Now, the second thing, what I said was we were looking on the temperature, and we had to change our lab setup a little bit. We were still, so this is a picture of our coherent module, and we needed a cooler and especially a heatsink. The funny story here is actually there was like some history involved. We took from an old Cisco 800 actually the heatsink and just placed it on the coherent module, and actually it worked. It was sufficient to cool it down with the fan combined. And the funny part here is a good friend of mine in Frankfurt area, because we were based in Germany, he basically decommissions equipment around Frankfurt and really separates everything in different parts, and I got a whole bunch of heatsinks from him. So if you ever need someone who takes care about your gear in Frankfurt, please ping me. And he's doing a really great job, really separating every type of material for some purpose. Okay, with that I hand over to Gerhard.
Thank you very much, and hello and bienvenidos. Before we get to the interesting experiments, I want to show the diagram version with a coherent transceiver, so it goes well with the first picture we showed. And you can see quite a difference now, because the advantage of the coherent transceiver is that it benefits from more properties of light, meaning that the recovery is way better, but you also are dealing with higher temperature. But that is normal, and as you can see in this diagram, the advantage is you don't have any strange jumps compared to the direct detection one we showed previously. So the correlation between temperature is not really noticeable. The only correlation that is left is the length of the cable, basically. And yeah, it's also a different range because of the specification of the coherent is also a little bit different. It can have a higher bit error rate because of the benefits that it reads out more the properties of the light, like polarization. It's better at recovering. No? The system is more complex, but it's better at recovering. But the trade-off also is that it gets hotter. As you see in the previous picture, we had to cool down the sky quite a bit more than usually. Right, and that is what happens when we remove the cooling. That's also very interesting with the bit error rate, and something I also want to communicate. You will see it in other diagrams. Bit error rate is a rolling average value. Here I started without the cooling. You see the values are slightly higher, but it is kept stable with increase of temperature, basically. And talking about temperature, I mean, this is one of the main parameters we have been talking about. And normally we are interested in our differential equation in boundaries. Boundaries means extreme values. And we wanted to see what happens when we bring up a transceiver up to 120 degrees. Don't try this at home. It is with barbecue and aluminum foil. And the only thing that is exposed here is a transceiver. It's a little bit hard to see. I used a little bit of Microsoft Paint to draw where the transceiver is, because with the gray and silver color, a little bit difficult to see. And this heat gun, don't use it with your hair, because it goes up to 600 centigrades. That's quite hot. So that is a special heat gun. And yeah, we brought up this transceiver and tried out, and we really wanted to see how it behaves, what happens, just to get a feeling, an experience, what would happen if, for example, you have a network gear and all of a sudden it starts to fail. What are the extremes? What can you expect of a transceiver? And here I did it in different stages, because, you know, we like to work in a secure environment. The warm-up is without the heat gun. I just let the transceiver becoming hot, warm it up. And at around 65 degrees, we just stop usually, because for us it is too much. But from the registers, you can read extreme values. High warning, high alarm is something you might have seen in your SROS, in your operating systems of the switch. So these are the vertical lines you see here, and we didn't reach it yet. Since we want to have a good lifetime, usually we are way below the high warning when we run our software. So I changed the code, I hacked it around, and this is phase 2, and I let it go beyond these 2 vertical lines to 100 degrees and see what happens. And you see there's a margin after high alarm, but after that you get a loss of signal. Then I let it cool down. I tried it again just to see if it still works. Did it break or did it not break? So I let it cool down a bit. I put a limit to 120 degrees, and that's a green small line. And like, it's the same behavior. Yeah? You go like 80 degrees and it's over. But it still works. It still recovers. And now I wanted to see how well does it recover, what are the consequences. And that is phase 4, I call it cool down. So after we reached the 120 degrees, I let it cool down a little bit below 70 degrees and was checking what happens. Afterwards, the transceiver still is very warm. The temperature increases a bit, but goes down again. This was without the heat gun. But you can see what is interesting, that this curve, this little bit strange curve, hits the other line. So we get back our original bit error rates before we brought it to the extreme, and after it's still with the same values. It's the same cable, 2 meters jumper cable. This still works out. So to be honest, I was a little bit disappointed by this experiment, but I'll get to that later. Another discussion is bit error rate recoverable. And this is a takeaway from you. We bring it up in the end. But what happens when you remove a cooler and put it back on? Or what happens if your network gear, the fans fail, or the heatsink doesn't do the job, it is dirty or whatever, your transceivers get too warm? And what happens if you do something against it and all is getting better again? Well, plugging out the transceivers might be difficult because it's running, it's transferring data. You don't want to do that. So the best is if you just can remove the fans. Sometimes you have like power supplies that you can swap out and it is all good. You can continue running. But you should keep in mind, while all the other values, like temperature obviously goes down again when you put the cooler back, but the bit error rate does not recover. And the reason for that is when you usually read it out of the register, it is a rolling average. The firmware checks the bit error rate, writes it into the register, and takes the old value, like takes the current value, add the new one divided by 2, whatever, what the rolling average does. And you have to keep this in mind. You can reset the transceiver, plug it out, plug it back in, and you get to the original values. But if you don't do that, you are dragging history with you. So just to keep this in mind. Do we still have time? Because I want to show you some experiment. And finally, my smartphone is charged again, so we can do a different thing with this device. And that is, I want to show you a little small Python script here. We are going to show the bit error rate in the live session and discuss a little bit what can happen. Yep. It takes a little bit to boot. I mean, it has to generate the PRBS on the DSP. Since it's almost like a small computer, it takes a little bit of time. But as you can see, it's doing its thing. Let me go here into full screen. Yeah, you can see it. And wait a bit. And when it is ready, it will start showing our bit error rate. So to the left, you can see the bit error rate. To the right, you see optical signal to noise ratio. And I have been checking the reception power and the temperature as well. I mean, it's good to monitor these values. Reception power on the photodiode side helps us a little bit to track the signal. And here we go. It booted up and it started to record. And as you can see, it behaves pretty normal. We had a temperature of about 20-something degrees, and the transceiver is getting warm a little bit. But it's not that bad. It should go. If you leave it running for a long time, in this case, with that transceiver, like 40, 50 degrees. And as you can see, the bit error rate also has an interesting behavior. It gets a little bit stable. And there's one challenge with measuring all this. You have registers where you read out the memory, but the thing is, media bit error rate and media optical signal to noise ratio, these two views we were talking in the first slide, share the same memory. So what you have to do is write into the register a value, it's a diagnostic selector, in order to swap. And that is what is happening here. It's swapping the diagnostic selector in the background, which means, yeah, the FPS could be a little bit, frame per second could be a little bit better. So I added this small button to just say, don't swap out, and you can see the curve is a little bit smoother. So that is something you have to consider, because if your switch is reading out these many values of your diagnostics, that is the reason why it might take more time, it might take less time. And one more thing I want to show here is, so you can see that this is not a pre-recorded video, that we do live things and interesting live experiment. Let me bend this cable and see what the consequences are. Oh, look at this. Oh. Yeah? What is the minimum value you get here? Which is almost loss of signal. Nah? Any idea? Can it go beyond minus 40? Minus 40 is usually the value where you can say no signal, right? So I bend it too much, but it's all good. It's elastic, so it goes back. And another thing you can see, the media SNR is interesting. It shows 30. Like, is it a better value? Oh, the signal to noise ratio is way better if I bend it. No, the value between 20 and 30 is the default value. You never go beyond the 30 in our transceivers. There's a reason for that. It has to do with quantum mechanics. I have no idea about quantum mechanics, but yeah, it's called the quantum error. It is because the recovery and the Gaussian noise you have is problematic. So suppliers, manufacturers usually try to drive between 20 and 30. Below 20 is bad, and beyond 30 is also not good. And yeah, that's all about this little live demo. Let's go back to some of our slides and wrap the whole thing up. No. Let me, yeah, here we go. Yep. I told you I was a little bit disappointed with the 120 experiment, so we ramped it up to 250 this time with a different transceiver. And it looks like this. You cannot even read the label anymore afterwards. But the more interesting question is, does this transceiver still work? Well, I was able to boot it up. I was able to read out the register. What I did not show here, but I will tell it to you, the reception signal was quite bad. So it is a functional transceiver, but it is a transceiver you don't want to use anymore. And I introduced a new value. I called it weird. It starts at 128 degrees. For the developers of you might know sign char or 8-bit values when they have a sign in the first bit. That's the reason why it's 120. You get negative temperatures. I corrected this in the diagram. So beyond 28 degrees, I corrected it so it looks positive, but really it was showing negative values. I called this section weird, and that's it. So you might read negative values if your transceiver gets that hot. So yeah, this transceiver is not usable anymore, but I think we learned from that, don't burn down your transceivers. Anyway, takeaways. Yeah, so you saw the difference between direct detection, transceiver, and coherent. The big advantage with coherent is they benefit from more physical properties, and you can see in the diagrams there are certain advantages. Bit error rate is always a rolling average value. Keep this in mind. So if it doesn't jump down to a way better value, that might be the reason, but that's not a problem. Yeah, and beyond high alarm temperature, if you hit the high alarm temperature, have a look at your transceiver, because beyond that there's not a big margin. And yeah, with that, Thomas.
Maybe some. I want to add something there on the third point about the high alarm temperature and the loss event. What Gerhard showed also, that the loss event actually was, so he was heating up to 120 degrees, but the loss event hit in there at 80 degrees. And actually this loss event was an artificial one made by the DSP. So it's a self-protection function inside of the DSP, so that it then shuts down itself. You get a loss, and then you as a network operator definitely will look at your gear, because otherwise when it gets too hot, the DSP will break. So this is more like a safety function of the DSP. And it's very close to the high alarm threshold, which you see on the diagnostic monitoring. On the coherent modules, yes, we saw it's more the distance, less the temperature, but I want to point out here the temperature part. For sure, when they are running too hot, it's not, or out of spec, it's not fine. It's more the temperature changes, and this is due to the effect of the properties of the light, which is not only the amplitude, which is used there for the coherent ones, it's also the phase and the polarization, which really ruggedize basically the signal a little bit. And finally, we saw a close relationship of the bit error rate to the signal-to-noise ratio, especially to the optical signal-to-noise ratio. So you, as a network engineer operating your gear, actually, when you run direct detection transceivers within a data center in metro distance up to 20, 30 kilometers, then there is nothing you have to worry about the SNR. So when the BR is fine, then your SNR is also fine. And yeah, that's it from our side. Thank you very much, and we are around until tomorrow. If there are questions, let us know. Thank you very much.
Thank you. Sure.
All right. Thank you, Thomas and Gerhard. Looks like we have some questions. Please state your, remember to introduce yourself and company you're representing before you ask your questions. Thank you.
Hi. Excuse me. I'm Brian Fields, Tampa Cooperative. So I had kind of a thought experiment here. I noticed that kind of everything goes, up and to the right in terms of bit error, Did you try cooling it down? Like,
this is a good
liquid nitrogen's cheap,
Yeah.
I'm just curious.
Yeah.
That's the engineer in me saying, well,
yeah,
let's try it.
Thank you very much for that great question. Actually, you're not the first one asking this type in terms of cooling it down, or even going to the minus degrees, what's happening there, and we haven't done it yet. That's the answer, basically. But it's an interesting one to see what's happening at minus 40, minus 50, and so on.
I think you got another presentation then.
Yeah.
And that'd be a hell of a demonstration to have on stage.
Especially here on stage. Yeah, I got it. Thank you.
Another question?
All right. Thanks a lot, folks.
Thank you.